next speaker is Alia Hamieh from UNBC, who will speak about quartic Gauss sums over primes.
Thank you. I'd like to start by thanking the organizers for the very kind invitation. I'm very happy and I feel very honored to have had the opportunity to participate in this celebration of Professor Ramurthy and his many contributions to the mathematical community. All right, so in this talk I will talk about sums of quartic Gauss sums when evaluated at prime arguments. This is joint work with Chantal David, Alexander Dunn, and Hua Lin. But to start with, I'll start by talking about the problem for cubic Gauss sums, because that problem has been studied extensively and it enjoys a very exciting recent progress. So I'll talk about that at the beginning. And then we'll talk about, I'll introduce the quartic residue symbols, quartic Gauss sums, describe our results, and at the end, sketch the proof of our main theorem in as much detail as the time permits. Okay, so to start with, cubic Gauss sums. So cubic Gauss sums are sums associated to the cubic residue symbol. So the notation here, so whenever we have okay, so E of x here is the usual e to the 2 pi I x, where when x is real. And this E of z here is e to the 2 pi I times the trace of z, for when z is a complex number. Omega is the third root of unity, e to the 2 pi I over 3. And this right here is the cubic residue symbol. So for integer c in zeta joined omega that is congruent to 1 mod 3 in zeta joined omega, the cubic Gauss sum is the sum we denoted by g sub 3 of c, and it's the sum over all d mod c of the cubic residue symbol d over 3 multiplied by this additive character. Now, the cubic Gauss sum satisfies many very interesting properties. One of them is the fact that when you cube it, you get mu of c times c squared times the conjugate of c. Mu of c here is the Mobius function for zeta joined omega. And so, for example, one thing that we can infer right away is that if c is not square free, then our Gauss sum is 0. If c is square free, then in absolute value, the cubic Gauss sum is equal to the absolute value of c. And so, which is the norm of c to the 1/2. You take the norm in the Eisenstein integers. So there's a natural normalization here. So we introduce the normalized Gauss sum, this here, G3 tilde, which is the original Gauss sum divided by norm of c to the 1/2. This way, this normalized Gauss sum has absolute value 1. And one thing also that one can infer from these two formulas here is that the cube of the cubic Gauss sum can be evaluated as mu of c times c over absolute value of c. This is going to be of relevance on the next slide because we're going to specialize it to c being prime. All right, so let pi here, consider pi to be a prime element congruent to 1 mod 3 in zeta joined omega, whose norm is rational prime p. And so the Gauss sum in this case, the Gauss sum associated to this prime element pi can be written as such. One can verify that, you can write it as such. And if you remember that formula at the end of the previous slide, if you specialize it to c equals pi, you get that the cube of the Gauss sum associated with pi is minus pi over absolute value of pi. Now, Kummer was interested in a question related to cubic Gauss sums. And the question was, is there a way to select which cube root of minus pi over absolute value of pi is this normalized cubic Gauss sum. Much like was hoping maybe to get something analogous to Gauss's determination of the sign of quadratic Gauss sums. But didn't work out for him. So he considered the problem. So he considered the situation is different for cubic Gauss sums. So instead he considered the problem from a statistical perspective. So he divided the primes in zeta joined omega into 3 sets, S1, S2, S3, according to whether the real part of the normalized Gauss sum is between -1 and -1/2, or between -1/2 and 1/2, or between 1/2 and 1. And then he computed these quantities right here. So the number of primes, the numbers of prime elements congruent to 1, 1, 3 in zeta joined omega, whose norm is less than x. So n sub S1, for example, would be those primes those primes that belong to S1, for example, and so on and so forth. So then he computed the first 500 of these and noticed that these normalized Gauss sums lie in these sets S1, S2, and S3 with statistical frequencies that are proportional to 1 to 3. And suggested, and according to Heath, Brown, and Patterson, one of their papers, they say he suggested hesitantly and cautiously that this might hold asymptotically. Now, in the 1950s, with the rise of computers, people did more elaborate computations, and then these computations cast some doubt on this prediction of Kummer. And then a folklore conjecture arose that really these values, the normalized Gauss sums, when evaluated prime arguments, they should be equidistributed on the unit circle. And indeed, Heath, Brown, and Patterson in 1979, they disproved Kummer's conjecture, and they showed that the values of the normalized cubic Gauss sums, when evaluated at prime arguments, are in fact equidistributed around the unit circle. Now, the way to attack this problem is through studying moments. And basically, it's an application of Weis equidistribution criterion, which tells us that you need to study moments of these values. And as it turns out, these moments, studying these moments will reduce to studying twisted first moments as such. Now, I will talk more about this relation between moments and these twisted first moments in the quartic setting. It will be the same for the cubic setting as well, but I'll talk more about it in the quartic setting. But, so the problem reduced to considering the asymptotic behavior of twisted first moments as such. L here is any positive integer. And the way, using Bayes' criterion for equidistribution, the way to show equidistribution is to show that the sum is little o of x over log x. And indeed, they showed, they did much better than that. So Heath, Brown, and Patterson, in that paper, they showed, they conjectured, they made a conjecture. So this is based on an earlier conjecture of Patterson in 1978, I think. So they made the conjecture, the refined conjecture, that this sum is actually asymptotic to some constant that they given explicitly. I just didn't write it down here. Times x to the 5 over 6 plus big O of x to the 1/2 if L is 0, and big O of x to the 1/2 plus epsilon is if L is non-zero. Which basically, so this x to the 5 over 6 expresses the bias of these values to being positive. And but they didn't show this in their paper, but what they were able to show is that the sum is less than x to the 30 over 31 plus epsilon. When L is not 0, when L is 0 and when L is not 0, you get that extra term. Heath, Brown then, in 2000, he improved, he refined upon this asymptotic, and he showed that the sum of cubic Gauss sums over prime arguments is indeed less than x to the 5 over 6 plus epsilon. So he was an epsilon away from that conjectured asymptotic of Heath, Brown, and Patterson. Now, there was some work in between by Coleman, I think, in his PhD thesis. And very exciting recent breakthrough, Dunn and Radziwill, they showed that they proved Heath, Brown, and Patterson conjecture under the GRH. Well, they consider a smooth version of this sum, but yeah. Okay, so I think that's what I wanted to say about this problem in the cubic setting. Now for quartic Gauss sums. So just so I'm make sure that we're all on the same page. I'm just gonna do a very quick overview of the quartic residue symbols. So here we work in Q adjoint I. Let lambda be 1 plus I. It's the unique prime lying above the ramified prime, the ramified 2. And so the quartic residue symbol alpha over pi is so given a prime element pi in Z adjoint I that is not associated with lambda. And given an element alpha, an integer element alpha that is relatively prime with pi, the associated quartic residue symbol alpha over pi is defined as such, the expected definition. Now, throughout the slides, we'll also see the quadratic residue symbol over Q adjoint I. So that's its definition as well. Now, the quartic residue symbol will take values in plus or minus 1, plus or minus I, and the quadratic one will take values plus or minus 1 as expected. And we can extend this definition by complete multiplicativity to all integer elements gamma and Z adjoint I instead of just pi. All right. If alpha and gamma are not relatively prime, we just set the quartic or the quadratic symbols to 0. And if you raise, this is a real, simple observation, but extremely important in our work, that when you square the quartic residue symbol, you get the associated quadratic residue symbol. And we also have a notion of biquadratic reciprocity here, expressed by this formula. So later in the slides, you'll see this quantity, this minus 1 to the power of c of alpha gamma floating around. Basically, this is this factor that appears in the biquadratic reciprocity. All right. So once again, same notation with these additive characters right here. So let C be an element in Z adjoint I that is relatively prime to the ramified element lambda. Now the quartic Gauss sum over Z adjoint I is defined associated with C. So we do twisted, I'm defining a more general Gauss sum here. That's where this nu comes in. So G sub 4 of nu C is the sum over all D mod C of the quartic Gauss sum D over C, and then sampled against that additive character. So, and similarly, we have a definition for the quadratic Gauss sum over Q adjoint I. Now, if nu is 1, then we're just gonna call it G sub 4 of C, just the regular Gauss sum. Analogous, which would be, a general, an analog of that cubic Gauss sum that we saw earlier. Okay, so many properties of this quartic Gauss sums that one could verify. So for example, we have this property right here. So G of R nu C is G of nu C multiplied by this quartic symbol. But more importantly, which, I mean, this property proved to be extremely important in our work, is that twisted multiplicativity of the Quartic Gauss sums. So G of mu C prime is G of C times G of C prime up to this factor right here. And using this identity along with this one can also arrive at this identity, which again turns out to be very important in our work. Now, one can show that, just similar to what we had, the properties that we had for the cubic Gauss sum, we can show that in absolute value, the Quartic Gauss sum is equal to mu squared of C times norm of C to the 1/2. Mu squared here, mu is the Mobius function for Q of I here. And so it makes sense to consider a normalized Gauss sum, which is essentially the regular Gauss sum divided by norm of C to the 1/2. Now, for the sums of these Quartic Gauss sums at prime arguments, what do we know? Well, Patterson in 1987 showed that the sum of the Quartic Gauss sums at prime arguments, well, given as such here. I mean, I'm saying at prime arguments because, you know, lambda detects the prime powers, but then G is only is supported on square-free integers. So really, this is detecting. This is a sum over primes. And he showed that these are less than x to the 19 over 20 plus epsilon. So one thing, so from that we can, well, his result is more general than that. First off, I only stated it in this way, but his result actually is more general. It's for nth Gauss sums, not just Quartic Gauss sums, and then he has it also incorporates twist. So in particular, his result actually gets that equidistribution of the nth Gauss sums on the unit circle. Yes. The 19 over 20 is there, but there's another term that, depending on n, might be dominant or not. All right, so we considered this problem, we worked with a smooth version of that sum, and we were able to get a refinement of Patterson's bound in the quartic case. So we showed that the sum of Quartic Gauss sums over primes with this additional twist here is less than x to the 5 over 6 plus epsilon plus x to the 3 over 4 plus epsilon times the absolute value of L to the 3/2 as x goes to infinity. So we can see that this, this improves the bound of Patterson. I mean, we do consider a smooth version of it, but we're hoping that, even if you want to remove that smoothing, we're only gonna lose just a little bit in the power savings, not much. Okay, but now this is not close to what we actually expect. We do expect this, so we make a prediction on the asymptotic behavior of the sum. And our conjecture is that the sum is asymptotic to x to the 3/4 times some constant b plus big O of x to the 1/2 plus epsilon if L is 0, and if L is non-zero, you get square root cancellation. So that's our prediction, but we're very far from having anything like that, even under the GRH. And the obstacle here, so we'll see actually in the next slide, or maybe a few more slides. The way to go about this is to write the sum as, use Vaughn's identity and write it as two types of sums, type 1 and type 2. The problem happens in type 2. This power of 5/6 is really forced on us because of the way we estimate our type 2 sums. The type 1 sum already give us an x to the 3/4. All right, but now here, as I promised earlier, I wanted to make a connection between these equidistribution, this equidistribution question and studying these twisted first moments. So Weil's criterion for equidistribution requires that if you want to show equidistribution, you want to get an asymptote, you want to show that the kth moment of these Gauss sums when evaluated at prime numbers, prime elements, is little o of x over log x. But now, as it turns out, now in this sum here, in our particular setting, so if you have a prime that is congruent to 1 mod lambda cube, its norm will be p squared for some rational prime p congruent to 3 mod 4, or its norm is going to be p, where p is a rational prime congruent to 1 mod 4. Now, this particular case here, when the norm of pi is p squared, we're going to just discard these primes because there aren't so many of them anyway, and they contribute big O of x to the 1/2 to that sum. So let's just assume that here we're summing over primes pi, whose norm is a rational prime p congruent to 1 mod 4. And in this case, actually, one can verify that the kth power of the Quartic Gauss sum evaluated at pi has this nice, closed form. So we see, for example, that if k is 0 or 2 mod 4, then our question really is reduced to sums of characters like that, and then you can get the bound that you want by using zero-free regions of the associated Hecke characters. And if k is congruent to 1 or 3 mod 4, then you can see from these formulas here, then you really reduce to looking at sums of this form. So the sum of the kth power of these Quartic Gauss sum reduces to twisted first moments as such. That's why we study these sums when we're trying to answer questions about equidistribution. All right, so now going back to our main theorem, how do we go about proving a result like that? The point of departure, just like in the work of Heath, Brown, and Patterson, in the work of Heath, Brown, is Vaughan's identity, because we're trying to estimate a sum over primes. And Vaughan's identity has proved to be an extremely powerful tool in understanding, in estimating sums over primes, because it allows us to decompose these sums into two types of sums, type 1 and type 2. Type 1 is usually a linear sum, and then type 2 would be bilinear sums. And the idea is that this helps us to drop that condition that we're summing over primes, so the sums become more tractable in a way. So wrote a bunch of sigmas here. So the notation of Vaughan's, the way Vaughan's identity manifests itself in this particular setting is as follows. So consider sums of this form right here. So sigma j would be sum of this form here. Remember, R is our smoothing function. It's supported on 1, 2. So really here you're summing over elements A, B, C, whose norm, such that the norm of A, B, C is between x and 2x. That's what we're summing over. So, so what do I mean by sigma 1? For example, sigma 1 would be the sum with A, B, and C restricted to the further condition that norm of BC is less than, when J is 0. I mean, sigma 0 would be this sum when a norm of BC is less than mu. And similarly, J equals sigma 1. Basically, we have this extra condition, and same for sigma 2 prime, sigma 2 double prime, and sigma 3. That's how Heath Brown uses it in his work in cubic Gauss sums. So Vaughan's identity is this relation right here. Now, as it turns out, we'll see in the next slide, the sigma 0 here, if you just rearrange the sum, sigma 0 is really the sum we're looking for, is that sum over primes. And sigma 1, sigma 2 prime will be what we refer to as type 1 sums, and sigma 2 double prime, sigma 3 would be the type 2 sums. So a bit of notation here. Have 6 more minutes. All right, we'll see. Now, what, 11? Oh, okay. The type 1 sums, sigma 1 and sigma 2 prime, with a little bit of work, one can show that they can be estimated by essentially estimating partial sums as this one here. So f sub beta of x is defined as such here. So this is the partial sum of these Quartic Gauss sums only over all integers. Over all integers c with norm less than x. With the extra divisibility condition, we're running over c's that are divisible by this particular alpha. So estimating type 1 sums and type 2 sums will amount to estimating really sums like this one here. And as I said, sigma 0, which is the first term that appears in Vaughn's identity, is essentially the sum, is exactly the sum that we're trying to estimate. So now Vaughn's identity reads as such. So that's what we want to estimate, and then it boils down to estimating the type 1 sums and the type 2 sums. All right, so let's see. For the type 2 sums, that's not how it shows initially after you apply Vaughn's identity, but with a little bit more work and rearranging the terms, you can write it as such. And what is really nice is that now we don't have the quartic residue symbol anymore. We end up with the quadratic residue symbol, which will help us immensely in estimating this type of bilinear sum. So these weights, these functions a of v and b of w, you don't need to know much about them except that there are in absolute value less than x to the epsilon. So that's number one. And they're supported on square free elements. Is there a sum missing in b of w? No. No, it's just that term. Yeah, just that term, yeah. All right, so in order to have a better control of our summation variables, we impose a dyadic partitioning, and so that our summation variables v and w that you see in the type 2 sums are of order of magnitude v, uppercase v and uppercase w respectively. And so what we do here is, in order to estimate this type 2 sum, I'm only showing some of the computations for sigma 2 doublet prime. The computations for sigma 3 are very similar. So what we do here, we take that, after we apply our dyadic partitioning, we take absolute value both sides, triangular inequality, and with a bit more work, so I'm skipping some steps here, but if we look at this if we look at this sum right here, so if we use Mellon inversion of the smooth function R, then estimating this inner sum reduces to estimating a sum of this form right here. Right? And in estimating this last expression that you saw on the last slide, we use a quadratic large sieve over Q of I. This is the generalization of Heath-Brown's quadratic large sieve over Q. So Onodera has the result over Q adjoined I, and then Goldmacher and Lovell have an even more general statement over any number field. But Onodera's statement will suffice in our setting. So you can see that this is a quadratic large sieve inequality that is of the same quality as Heath-Brown's original quadratic large sieve. So So what we do is that if you look at the sum right here, which is what our estimation of the type 2 sum boils down to, and we apply Cauchy-Schwarz. Before we apply that quadratic large sieve, we just need to know that, all we need to know about that these functions A of V and B of W, again, they are, the weight functions here are supported on square-free elements, and they're very small in size. They grow at most as x to the epsilon. So doing this and applying this quadratic large sieve that we saw on the previous slide, we get this estimate. For that, this is the innermost sum in the type 2 sum. And putting things together, we get this estimate for our type 2 sum. Then you can see that if you choose u, so u here, this parameter u, you could choose anywhere up to x, but really we're gonna go up to x to the 1/2. In our previous setting, actually, we required u to be less than x to the 1/2 because there was an extra sum in Von's identity, which is sigma 4. And if you assume that u is less than x to the 1/2, then you can just drop that sum. We did that. But here in particular, if you choose u to be x to the 1/3, then you would get that x to the 5/6 term that you saw in our main result. Okay, so now for type 1 sums, and that's where usually in Heath-Brown's work for cubic Gauss sums, the intricate part was dealing with the type 2 sums because he had to prove a cubic large sieve inequality in order to deal with the type 2 sums. So that was the most involved part of his work. The type 1 sum was already very well established in Patterson and Heath-Brown-Patterson old work, so that one did not require that much work. Now, in our case, we borrowed Heath-Brown's methods and argument for the type 2 sums, so that wasn't that bad. Now, with the type 1 sums, however, things become a little bit more intricate. Because we have to deal with Dirichlet series whose coefficients are Gauss sums, are quartic Gauss sums. And we need to understand the residues of these Dirichlet series. And as it turns out, the residues of these Dirichlet series can be interpreted as free coefficients of certain quartic theta function over the fourfold cover of SL2Zi. And these are not fully understood, but luckily, whatever is known about them is what we needed. We need more. Let's see how much I can say about that. So the type 1 sum here. So again, as I showed in a previous slide, estimating the type 1 sums boils down to estimating some partial sums like that. So sums of quartic Gauss sums, partial sums of quartic Gauss sums over all integers, essentially. So when we have something like that, it's only natural to look at the Dirichlet series associated with this partial sum. And that we call f sub beta of S alpha. And so again, this is the Dirichlet series with coefficients being the quartic Gauss sums, with the extra condition that alpha divides our summation variable. And we do a bit of manipulation here of this sum. We go back to the original Gauss sum. And this right here will be denoted by psi sub beta of S plus 1/2, 1 alpha, right? The one here, this one here is because we're doing, the untwisted Gauss sum. If we had an U, if we were doing G sub 4 of nu C, then we'll have a nu here. And as these Dirichlet series have been studied by Kubota in the 1970s, and then by Patterson a little bit, by Suzuki in the 1980s, and very recently by Diacono, just to mention a few. And they appear as the Fourier-Whittaker coefficients of certain metaplectic Eisenstein series. And that's the way to understand the residues, really. You need to go the automorphic route to understand the residues of these Dirichlet series. All right. So as it turns out, one can show that these Dirichlet series has a meromorphic continuation to the entire complex plane with a possible simple pole at S equals 5/4. And the residue will be denoted by P sub B of 1 alpha in this case. So again, if you look back at that partial sum, almost there, okay, I just need maybe just a minute. All right, if we look back at this partial sum, we use Mellin inversion, and we write it in terms as a contour integral involving the associated Dirichlet series. We move the line of integration to the left, and we pass the pole of that Dirichlet series at S equals 3/4. Remember, we're evaluating psi at S plus 1/2. Psi has a pole at 5/4, so that's where S equals 3/4 came from. 3/4 plus 1/2 is 5/4. So when doing so, you capture that residue right here, and you end up with a leftover contour integral, and just some error term. And this is basically, thanks to the rapid decay of the Mellin inverse of R, we get a very small error here. So now we need to understand the contribution of that main residue part in that contour integral. I'm not going to talk about the contribution of the contour integral, although its contribution, the estimation of its contribution is quite intricate. But I will talk about the contribution of that residue term. And essentially, this is where we get that x to the 3/4 that you see in our main result. But, and you can see really what we need is the fact that this residue is less than 1/norm of alpha. And in order to do that, that's where we needed Suzuki's evaluation of the residues of these Dirichlet series. I'm running out of time here. So essentially what happens is that you relate these Dirichlet series with the Dirichlet series but without that divisibility condition by alpha. And what saves us really is this squares here. The fact that, we're having this Dirichlet series at m squared nu, because, so we're looking at the residues of these Dirichlet series, and it turns out that Suzuki has a closed form evaluation of the residues of these Dirichlet series in this specific case that appears in our computations. And he has these evaluations as such. And just working with Suzuki's exact formula for the residues of these Dirichlet series, we were able to get that bound of 1/norm of alpha, that we used in the previous slide. And putting things together, you get x to the 3/4 plus epsilon, that's coming from the contribution of the residue term, and then x to the 1/2 plus epsilon u to the 3/4, that's coming from that contour integral that I didn't talk much about. And so combining the estimates for the type 1 and the type 2 sums, we arrive at the main results. Thank you for listening, and happy birthday.
Thank you. And we have just a short amount